Greetings, everybody. This is Greg Freeby with the American Segmental Bridge Institute. We're going to probably start the webinar in about another 2 minutes here. Just wanted to chime in and give you all an opportunity to adjust your volumes on your computers. And again, we'll get started here in just a minute. Greetings, everybody. It's straight up the top of the hour, and we're going to go ahead and start today's webinar. Hopefully, you are here today for the May webinar of the American Segmental Bridge Institute. We'll be introducing our speaker here in just a minute. I have a few announcements to make, some background on how the webinar is going to work today for those of you who haven't attended before, and then we'll move on to our presentation. Again, I'm Greg Freeby. I'm the Executive Director with the American Segmental Bridge Institute. You can see my email address here on screen. I'd also encourage you, if you're on LinkedIn, to follow the American Segmental Bridge Institute. And if you want, you can also look me up and follow me as well. At ASBI, we tend to have quite a bit of information going up on our LinkedIn page about new publications and webinar opportunities such as this one and other activities. So it's just a good place, in addition to our website, to get information on what's happening at ASBI. So some quick announcements. The first is we have a new publication on guidelines for design and construction of segmental bridges for rail. That is segmental bridges that support rail structures, whether it's transit rail, heavy rail, people movers, those kinds of things. And you can find that publication as a free download on the ASBI website under that publications tab. And then in June, our monthly webinar, we're going to be talking about the guidelines for construction and design of segmental bridges for rail. This won't be a chapter by chapter or page by page walkthrough of the manual, but more an overview of the information that's found there and what makes segmental bridges unique as far as their use to support rail. Another upcoming event we have is our construction practices seminar. We're hosting a session August 15th through 16th in Seattle, Washington. If you're on the West Coast, I'd encourage you to seek out this opportunity. Registration's up on the ASBI website. And I get the question a lot about, well, who should attend this construction practices seminar? It's an in-person seminar, and it's really a great opportunity for owners, contractors, and designers, pretty much everybody that is involved in a segmental bridge project. It's a fairly intensive seminar. We get into a lot of detail about segmental construction methods and some case studies. So if you want to learn a lot more about segmental construction, it's a great opportunity. For those of you who are infrastructure owners that might be online, registration for you is free. And so I'd encourage you and your staff to attend. I know we're planning, the folks from Washington State DOT are planning to join with a number of us. Number of their staff will be joining us for the I keep saying webinar, for the in-person seminar. And then later this year, I want to just put in front of you all our annual convention, October 31st through November 2nd at the Hyatt Regency in Austin. Our technical program is soon to be published. When you see it, you'll see we have a really great program this year. We have a number of international guests that will be speaking as part of our program, giving updates on some of what's happening in Europe on not only segmental, but post-tension construction, some of their new innovations. So again, encourage you, if you're put this on your calendar and plan to join us, registration should be up very soon on our website. So some quick instructions about how the webinar is going to work today. Some frequently asked questions. If you lose connection during the webinar, you can rejoin. Just use the link that you were provided. You're certainly going to miss content while you're gone, but you'll be able to rejoin. With that in mind, we will be issuing certificates for attendance, but only to those who meet a minimum required time in the session. Our license with RCEP requires that we have sessions of at least an hour in length, and we want to ensure that folks are, if not exactly at the hour, as close as possible to an hour of attendance. With regard to their certificates, please allow a week to receive those by email. If a week goes by and you still haven't seen your certificate, then certainly reach out to us and we'll see what happened. After this session, hopefully by tomorrow or by the end of the week, we will have on the web page available access to the recording as well as a PDF of the slides. Will be available on the events tab. There'll be some other resources uploaded there associated with this particular webinar. So again, give that a few days and those resources will be up. We will do Q&A at the end of the presentation, and I'll illustrate how that works on the next few slides. If you're working from a desktop computer, you should have in your little dialog box, the GoToWebinar dialog box, a little questions click. You can hit the little questions box and then type in your question in the box. What we'll do is we'll hold questions until the end, and then we'll do a Q&A session like you would at an in-person seminar. If you're on a mobile device, you should have a little question mark in the upper right-hand corner. You just click on that question mark, and then you'll be able to type in a question. We do at ASBI meet the requirements for continuing education through RCEP, and again, that's the entity through which you will get your certificate will be issued through RCEP. So again, give us a week at least, and then we'll to get your certificate out to you. So with that, I'm going to introduce today's speaker and then turn over to Dr. Washer. So our speaker today is Dr. Glenn Washer. He's a professor at the University of Missouri in Columbia. And before joining the university, Dr. Washer was at the Federal Highway Administration at the Turner Fairbank Research Center, where he served as the director of the FHWA Non-Destructive Evaluation Program. His research interests are focused on condition assessment of civil infrastructure, not just bridges. This includes developing non-destructive evaluation technologies for damage detection and also reliability of inspection technologies and risk-based inspection. And in the area of risk-based inspection, Dr. Washer was the principal investigator for NCHRP 1282, which was titled Developing Reliability-Based Bridge Inspection Practices. And the results of that research project actually were just recently published in the National Bridge Inspection Standards as part of the national requirements. Where that ties into what you'll hear about today is then Dr. Washer was able to leverage a lot of those techniques to develop a methodology for risk assessment of post-tensioning tendons. Dr. Washer was also the principal investigator on NCHRP 12104 about improving the quality of element level bridge inspection data, and this has been adopted now into the AASHTO manual for bridge element inspection that was approved in 2018, so now is being used throughout the US, actually by all states. His research in NDE technologies currently includes ultrasonic stress measurements, ultrasonic testing for steel bridge fabrication, thermal imaging technologies, and reliability of NDE technologies. He's published over 120 journal and conference papers related to condition assessment of bridges and is a fellow of the American Society of Non-Destructive Testing. Dr. Washer received his Ph.D. in materials science and engineering from the Center for Non-Destructive Evaluation at Johns Hopkins University in 2001. And so we have a really great speaker with us today, and I'm certainly looking forward to Dr. Washer's sharing with us the research results about this methodology for risk assessment of post-tensioning tendons. And so with that, I will unmute Dr. Washer and turn it over to him.
All right, thanks, Greg. I think that hopefully everything's working.
All right. Yep.
You could
we are hearing you and seeing your slides, so all good.
That's all good. So, well, thanks for that introduction, Gray. Yeah, I'm Glenn Washer, as he mentioned, and just put in an introduction slide that's got the same stuff on it he just talked about. Essentially, I'm a professor at the University of Missouri, and I've been here since 2004. And before that, I was with Federal Highways, and I did my work in non-destructive evaluation through most of my career. So that's kind of my area, and risk-based inspection works along with that. And I did my Ph.D. work actually on measuring force in post-tensioning tendons. Other than that, I'm not the post-tensioning guy specifically. I'm an NDE and reliability person, so to speak. So, and you can probably tell that based on the introduction. So, this is a very interesting project for me to work on, to take some of those concepts from 782, that report that was issued under NCHRP and is now part of NDIS, and apply it to this problem for post-tension bridges. In terms of our agenda for today, I'll talk a little bit about just the background of risk-based decision-making, which a lot of people may be familiar with, but in case you're not, sort of decode some of that risk language, and talk about this methodology for risk-based assessment of post-tensioning tendons, what that process is, what the attributes are that were identified in this process. And I'll go pretty quickly through there. There's a lot of text slides in there that I think they're there for the record, but I'm not going to speak to all of them because we'd be here for too long. And then a little bit of just an illustration of an example bridge, what this looks like if you do different kinds of corrosion protection strategies in the design phase of your bridge. So just in terms of background on the project goal was to improve the durability of post-tension bridges. The objective was to develop a guideline for conducting risk assessment of PT tendons. And this guideline is aimed at aiding designers to select corrosion protection strategies. So something that you would do before the bridge was open, while you were going through the design process and making decisions about what specifications might apply and things like that, what kind of technology you might have, or what design choices you might be making. And so that's one part that's kind of important. The scope of the risk assessment is really intended for designers. And I think there's probably a lot of concepts and even attributes could be applied to in-service bridges, but this one was intended for the pre-construction analysis of what the corrosion protection strategies might be for a particular bridge. And this is, as Greg was mentioning, this was done under work in Federal Highways under Reggie Holt's program. WSP was the prime contractor there. And the report, which I think is also in the link here, but is also available on the ROSAP website if you want to get a copy of those guidelines. Our first section here is just to talk a little bit about what is risk-based decision making and how do we use this in engineering, because everything these days seems to be a risk-based process. So I think people are more familiar with it now than they used to be. But one of the hard things, particularly in people that are in engineering, they want some quantitative values, and a lot of risk is assessed where quantitative values are unavailable. But really, the risk assessment is just a way of formalizing decisions that engineers make every day. We may not formally consider specifically the likelihood of something happening and what its consequence might be, but informally we do, just in the decisions we make about what bridges ought to be repaired, what bridges ought to be rehabilitated, and things like that. How important is this particular damage in this particular bridge? It really shakes out to just a couple of basic questions. What can go wrong? For example, if you had a steel bridge member, well, it might crack, for example. What are the chances of that happening in the next time interval? And the time interval is something you have to select somehow, either 1 year, 2 years. When we were looking at bridge inspections, we looked at like something for 6 years, or is it indefinite? Just sometime in the future, it's going to happen. That could depend on things like the loading that the structure's experiencing, if it has existing damage, or if it's got resistance to a particular damage mode that you're talking about, like consequence. And putting that together, like cracking rather, and putting that together with the consequence of the damage. What's going to happen if that damage were to occur? And so that kind of is a mind exercise in some senses, right? The intention is not that you're going to let the damage occur, but if it did occur, what would happen? Would it be really serious, or would it be relatively benign? It's a risk-based process that you're trying to put some order and formalize that somehow. And we go utilize this equation here. I'm going to just try to get my laser pointer going here. That it's the risk is some measure of a probability of failure times, and we use times sort of liberally here, times some sort of a calculation of what the consequence might be. So POF, that's probability of failure. that can be expressed in a series of different ways. You might call it the likelihood, you might call it the frequency of an adverse event. We tend to use a term like occurrence factor. How likely is it to occur in some particular time interval? That takes the word failure out of it, which makes people more comfortable sometimes. So, you know, a lot of different terms might be used for that, but that's the basic risk model. In terms of this probability of failure, well, that's easy to say, but it can sometimes be hard to apply. You need to define what you mean by failure. Do you mean the bridge is going to collapse? Or do you mean the bridge is going to require closure? Or do you mean a repair is going to have to occur? An occurrence factor, this term is used as a sort of stand-in for a probability of failure that considers the likelihood over some time interval. How could you determine the probability of failure? Well, if you were making widgets for a living and you could test 10,000 widgets and get a time to failure for a widget, that would make it easy, right? You could test the failure components and know exactly what their life is. That's not really practical in civil engineering. In most cases, we don't have tests for all these things. A lot of different systems are working together. You could use deterioration models if you have good quantitative data from the past. Or you might have to rely on experience in engineering judgment or expert knowledge. And this is what's been done, you know, in this project and also in risk-based inspection for regular routine bridge inspections to try to characterize what are the characteristics or what we call attributes of a reliable tendon, for example, or what are the characteristics might increase the likelihood that that's going to fail sometime in the future. Another option is to just use a point estimate. That's you've done a lot in the nuclear field and aerospace also, to just say these particular components have a, say, 1 in 10 to the 5th likelihood of failure over a 1-year time interval or something like that. We really focus in these types of technologies here on the engineering and expert knowledge. The framework that's produced, you know, if you have quantitative data about something, that could be integrated in, but it based largely on qualitative information. In terms of consequences, well, there can be different consequences for different risk models. They might be economic. What is the cost of this damage? Environmental, if it has some environmental impact, like a leaking gas pipe, for example, or something to do with safety. Is the bridge going to fall down, or is it going to be closed, something like that, or some combination of those? And, you know, it's just, as I said, it's very much, it's not different than what engineers do every day. Consider what are the consequences of this particular negative outcome. And so we combine those two and we determine a level of risk, either qualitatively, like low, moderate, or high, or quantitative, if you want to use a relative risk value, which is a quantitative way of using qualitative information, or if you have quantitative data, you could use that. We tend not to have a lot of quantitative data amongst any of the engineering systems that are made up of lots of different components. So, you know, what we're using here is a more qualitative risk assessment process. It's modeled after what's used in the petroleum industry, chemical industry, and nuclear industries in terms of how to utilize expert knowledge to develop a model that can be used to analyze risk. What do you do with this data once you figure out what is the probability of failure, what is the consequence? Well, there's different ways to implement that. One would be with a risk matrix, like shown on the right here, where things that tend to the upper right corner have higher risk, things that are in the lower left corner tend to have a lower risk. This matrix is just a consequence factor on one axis, an occurrence factor or probability of failure on the other, in this case, categorizing it into 4 bins. Now, this could be 4 bins, it could be 6 bins, it could be 8 bins, right? It depends on how fine of a model you might like to make and how well you think you can characterize what the risk might actually be. Or you can do it on a number line, which gives, I think, a little more flexibility sometimes, just taking whatever factors you consider and putting them into a quantitative model that you can scale on a factor of 1 to 100. Okay, so that's kind of a little bit of background on risk. And so basically the idea here is that we're going to take some measure of what the likelihood is of a particular damage mode occurring, some measure of what the consequence would be if it did occur, and come up with a risk level for a particular element or project. In this case, post-tension tendons. And in this case, the damage mode considered as corrosion damage during the life of the structure. And so in this section, we just want to talk about what the guidelines are for the risk assessment of PT tendons that were developed, how to apply the process, and how to evaluate a consequence factor and occurrence factor for post-tensioning tendons. And this is kind of the, well, how does this work? What are the mechanisms here? Well, we've used the mechanisms and processes developed under NCHRP 782, as you mentioned earlier. we've applied that just to assess the likelihood of corrosion damage and its risk for PT tendons. And it's a scoring process that's based on attributes or characteristics and criteria formed by expert knowledge and input. And so we have an expert panel that came up with these various attributes that I'll discuss. We identified what attributes contribute to the likelihood of corrosion damage, and also set up a system by which you could assess what the consequences of that might be in a relatively simple system that just relies on redundancy, replaceability, which is kind of a cost measure in a sense, and then the importance of the structure. The whole objective of all of that is to try to provide guidance on what you should be investing in risk reduction or mitigation strategies based on that assessment. So you can see it's really a way of, some would say a risk process a lot of times is kind of like a totem pole. You're just trying to figure out, which head on the totem pole are you, the one near the top or the one near the bottom? Is it a high risk situation which you might need to mitigate that risk through improved corrosion protections, or is it a low risk situation lower down on the totem pole where you don't have concerns in that area? The expert elicitation process was used. This is just a way of getting together a group of experts, asking some semi-formalized questions to stir discussion and try to identify, well, if you had a post-tension tendon and you had to assess its likelihood of corrosion damage during its life, what factors do you think you would want to know in order to make that assessment? Okay, and so we try to identify credible damage modes and what are the deterioration mechanisms. In this case, we really just have one damage mode, which is corrosion of post-tension tendons, and we try to identify key attributes for that, the reliability of those, and then rank those attributes and identify what the consequence factors are. And it's really a consensus process. It's done with a lot of white sheets. You sort of see a picture here on the right of the panel with a lot of those big white sheets with markers on them up around the walls in the room to discuss through what these attributes might be and what their criteria might be. And so as we go through and we get to where the attributes are discussed, you'll sort of see some flowcharts that sort of illustrate how that works or how that comes out in the end. Okay, and so the RAP team in this case had representatives from ASBI, PCI, Federal Highways, and State DOT, and some consultants. So it was a good group of folks. They were all experts in post-tension tendons. I'm not an expert in post-tension tendons particularly, but they were. So that's what's important. And they're familiar with the design practices, history, and what sort of unique circumstances might have arisen in the past. And so the idea of the RAP meeting is sort of gather that together and make an expert model. And we follow this same model I mentioned before. What can go wrong? How likely is it to happen? What are the consequences of that? Okay, and use those three questions to develop a semi-quantitative methodology, which is quantitative in the sense that it involves numbers, but it's numbers assigned to qualitative risk levels. Okay, and the idea is to have a rational process that in the end gives you something that's based on engineering judgment that can formalize that process and give you a score and improve decision making. Okay, so in our case, as I mentioned, what can go wrong? Well, we're looking at corrosion damage in post-tension tendons that would require a tendon replacement. That's sort of our assumed damage mode and failure criteria. Okay, and we brought this to the panel, and so everything sort of from here on is results from that RAP meeting, and asking a series of questions to these experts about what the damage mechanisms might be that would result in the damage mode of corrosion in post-tension tendons. So they came up with 6 areas in general. Breach duct or anchorages, it's water leaking into the duct or an anchorage. Quality issues with construction or workmanship. How aggressive is the environment that surrounds the bridge? Are there adequate specifications and detailing requirements included in the bridge to prevent the ingress of water and corrosive materials? Are you using poor or improper materials? And what is the likelihood that voids might be produced in a grouted tendon based on the factors that might contribute to a void being generated? So we'll talk more about those as we go along there. And so we use those 6 basic damage mechanisms to look at attributes for the post-tension tendons that might contribute to those different damage mechanisms occurring. Design characteristics, what specifications are applied, what is the exposure environment, etc. Those attributes are then ranked by the panel as high, moderate, or low based on how much impact they'll have on the likelihood of corrosion damage occurring. So if you look, for example, at a damage mechanism that we talked about, like voids and grouted tendons. So what are the characteristics or the attributes of a post-tension tendon that would increase the likelihood that a void could form? And so they came up with 4 attributes here: tendon profile, whether or not there's proper venting in the tendon, the quality of the grout used, and the grouting procedure used. Those are all things that could contribute. And so if we had those as attributes, and then we had some criteria for scoring them, right, that would be initial part of building this model for this particular damage mode. And I mentioned before, damage mechanism rather. I mentioned before there was 6 of those analyzed by the RAP panel. Okay, and they were analyzed and ranked, and then criteria developed for them. So in the end, they ended up being 19 attributes that fit into those 6 different damage mechanisms that I discussed. And they got reorganized sort of through the process to put sort of apples with apples and oranges with oranges, if you would, into these various areas: post-tension tendon and profile characteristics, joint enclosure characteristics, materials and components, what is the quality of the insulation and the environment that surrounds the bridge. So there ended up being 19 of these attributes. And so that's quite a few. And they were ranked in terms of their importance relative to the likelihood of corrosion damage. So you see over here on the right in this table is a ranking, and they rank from low, moderate to high, and some of them with a very high as the most critical characteristics that might contribute to them. And so, you know, just to sort of the 10,000 foot view is, okay, we've got these 19 attributes, we're going to score them, and we score them in a particular system. And things that have a lot of negative attributes, well, their likelihood of corrosion damage is going to be higher. Things that have very few negative attributes, well, their likelihood is going to be lower. That's the overall concept of what we're sort of trying to do here. And so criteria were developed for each of these attributes. We assign a point scale on that. Generally, something that's high, we give 20 points. Something that's low is 0 points, and something that's moderate is 0 in between. And then if the attribute itself is high, moderate, or low, well, we scale that. And so that's just a way of starting out the model to get some points scoring system that represents the relative weight of different attributes in their criteria. Along the way, as we built the model and analyzed, and I'll talk a little bit about some sensitivity studies done with it, some of those weights were modified a little bit from what the RAP meeting came up with. Things like vertical profile or microenvironment had their values adjusted based on their impact on the overall model as compared to engineering judgment of what their impact ought to be. We also use some add-ons just to calibrate the model and apply some engineering judgment to some particular things along the way. One example was, well, one of the characteristics was the likelihood that there was going to be a ingress of water and corrosive products at a closure pore. And if you had one closure pore as compared to having 2 closure pores, well, you'd say the likelihood is probably less. If we only have one of them, if we have twice, we have more likelihood that that's going to occur somewhere on the bridge. And if we had 15 closure pores, well, that would be a lot more, right? And so we needed some way to calibrate for that. Well, if you've got, you know, more than 3 closure pores, for example, or more than 2 closure pores, we want to adjust that weight a little bit to make that have a larger impact on the overall model. And so those are kind of details that went into developing the model. I think, to me, that looking at these types of models in this form of this sort of flow chart is a good way to help you understand it. You've got a category like PT tendon and profile attributes, and then there's particular attributes that go under that category. Let's say tendon length, tendon vertical profile, and tendon curvatures being 3 things that affect the likelihood that there's going to be corrosion damage. And then for each of those attributes, there's a series of criteria. Well, let's take tendon length just as an example. If it's a very short tendon, well, that's going to be low. It's not going to have a great, you wouldn't expect that to increase the likelihood of corrosion damage over its life. But if it's a very long tendon, well, there's various issues with stringing the tendon, getting it grouted, all those other types of issues. So that's going to be relatively high. Now, that doesn't make the risk of that bridge necessarily high. It makes the risk of that attribute high. It's going to contribute into a scoring process. It's going to consider all the other attributes as well. And so if you look over here on the right, these are the points assigned are on the right here. Okay, into the model. And we're going to sum all those things up. I'll talk about that in a second. Okay. Okay, so the results from that, constructing that model, determining the attributes, determining the criteria for the attributes, is then put into just a simple spreadsheet function that has pull down menus that you can take and apply those different criteria to. So it fills in the appropriate score. It also links to a commentary that's available, so you could link if you wanted to know what attribute A2 was, for example, it would link to commentary. I think I got an example right here. For example, here, if you clicked on A1 up here in this spreadsheet, you'd get a description of what that is meant to be, right? So it's a tendon length, and it just states what the rationale is for that particular attribute. So you can go through these 19 and look at what their rationale. Why is this in the model? Why is it scored the way it is? And they're mostly short blurbs, sort of like this one. Gives you the criteria on the bottom, gives you the description up above. Okay. All right, so we take that model and we just do a very simple thing. We just sum up scores, right? What are the total number of points available? How many points did this particular tendon score in that process? And if it has a lot of negative attributes, it's going to score high. This is I think it says on one of these slides somewhere, it's a little bit like golf. High score is bad. Okay, so you could do it either way. We chose to do it this way. So the more points you have, the worse it is in terms of the likelihood of damage occurring. And so if you've got lots of attributes that score kind of poorly, you'd end up with a really large score. And that would cause you to have a higher occurrence factor in this sort of a model. Okay, so if you look at this equation, so I work for a university, so we got to bring some equations of some sort, right? All this says you're going to sum up the individual scores and divide it by the sum of the overall scores. So summing up all the maximums it could be. So you get, maybe there's 300 points in the model. This particular tendon score is 120 points. You put that into a particular category in terms of risk. Okay, so you can put that into one of four categories if you're using a risk matrix, or you can combine it with the consequence if you're using a risk scale, which is just a scale from 0 to 100. And then there's the consequence factors. It's sort of other part of that model. If the damage was to occur, what are the possible consequences? And you want to use that type of scenario to try to focus on the damage that's most important. In this case, we're doing corrosion damage in tendons, so we sort of know what the damage is that's most important, but whatever its consequences. And so the RAP considered consequences of tendon corrosion damage in terms of three primary factors. Tendon importance based on a system redundancy factor, and these are factors that are documented like in the manual bridge evaluation, and they're referenced in the document. If you get the document, you can see where they came from. The ease of replacement of a damaged tendon, and so this is basically, well, is it an internal tendon or is it an external tendon? Is it designed for replaceability, or is it going to be a huge job to try to replace this particular tendon? And the third one was importance of a bridge. Is this along a key transportation corridor with a high ADT? Is this a very critical bridge, or is it not as essential a bridge? And the idea is that's something owners could use or others could use if they wanted to, as sort of an optional factor to contribute to the consequence if they felt it was appropriate within their system. Okay. So as I mentioned, that only three consequence attributes were used in the model. This redundancy measure based on number of tendons in the web, for example, and what the structural rating factors are from the manual for bridge evaluation, load rating, and box girder section, and I think one document that was published in Florida. Some measure the replaceability, is it internal, external, and a bridge importance. Just a note, this is maybe too fine a detail for this presentation, but the two of the attributes, the redundancy and replaceability, they're scored on a scale of 30, 20, 10, so that nothing would have a zero consequence, because that wouldn't really make sense in a way. Nothing is totally without consequence. And the third consequence that describes the importance of a bridge is optional. That one scored in a 20-10-0 score. Okay. And so we do the same thing with the consequence factors. If you want to put it into a category, right, you just take whatever our score was divided by the total available score, and that places you on a number line somewhere. Okay. This is just a flow chart that shows what these three are in terms of their criteria. So tendon importance, ease of tendon replacement, and bridge importance down here. And these are what their criteria are, and here's how they score on the right. Yeah. Let's see. All right, so once you've done both those parts, right, you can plot that into a risk matrix like I've shown here, or along a number line, which is just an expression of that on a value from 0 to 100. It's increased resolution if you use a line. You've got some more flexibility. In the matrix, there's really only 16 possible results, and you get a lot of things that are sort of on borderline. If you use a scale, you've got some more flexibility. You can sort of say, well, these things that score really low down here, 20 or below, those are our low risk ones. Then we've got a moderate range in here. We've got an elevated range. Now, we did determine criteria and set levels for this based on sensitivity study. In the sensitivity study, look at different scenarios of, well, if it's a PL1 or if it's PL2 applied to this bridge, what would be the outcome of this model? And we sort of went through with various of the attributes, increasing their values to look at, well, how does this score out in the end, if you will? And this is kind of a brute force method of doing it. Run lots of models with different combinations of what, let's call them negative attributes, or attributes that would increase the likelihood of corrosion damage. We used 8 reference cases of that with different tendons and attributes applying. Ones where we had, for example, it's a bridge built to PL2, and all the PTI ASBI specifications are followed in that bridge. And then maybe scenario 2 as well, it's PL2, but it's got poor quality attributes. And essentially, if you go through these 5 models, you're getting higher and higher risk as you go down to see what these examples yielded in the end. We also looked at different scoring approaches. How do these agree with our engineering judgment of what they ought to be, and just in order to calibrate that and maybe adjust some scores. Overall, there's like 500 different cases were looked at and scored in different values. And there was use that to determine an optimum scoring case, and also to set where the different risk levels would be. Okay, and looking at also the different consequence factors that were possible, and then use that to make models that show, well, okay, for different values of the consequence factor, which are shown up here, and scoring case 7, which is the one that sort of came out of the sensitivity study. What are these outcomes for these different scenarios as you get increasing likelihood of risk, or likelihood of corrosion damage, and use that to set some thresholds on where these models ought to be produced that agreed with engineering judgment. Okay, so it's going to be a little quicker. I think I've talked a lot about the process. Here, we just want to understand what the steps are required to complete the risk assessment and how to apply that. We've got an example coming up here. So the idea here is, and I think I've got a spreadsheet. Here we go. I'm going to start with this. I think this probably makes more sense. You know, we're going to take here, we've got an initial bridge design. We want to look at a particular tendon in the bridge that's going to be built later, knowing what our corrosion protection strategies are. Is this, are we following all the, say, current PTI and ASBI specifications, or do we have particular ones that are different, or we're not following that? We're sort of following the state's specifications. And take each particular tendon, and you sort of analyze it on a tendon by tendon basis, although, you know, many of the tendons obviously will have the same attributes, so they can be grouped together. And so you look at these different attributes that you've got in that of the 18, 19 attributes that we have, come up with a risk assessment score for that, okay, of what the occurrence factor is, what the consequence factor is, and that sort of provides you a risk profile. Now, if you're in the moderate to high risk range, the idea is that, well, that says, you know, you really should look at adding some corrosion protection relative to what you're currently using. And that might be a risk reduction strategy or a mitigation strategy. You know, reduction strategy, like get rid of corrosion altogether, use composite tendons or stainless steel, for example, or just adjust the mitigation strategy. That is, how do we mitigate this, improve, for example, the venting protection in the bridge, okay? And then redo the risk assessment until you get into a low risk profile, okay? And once you sort of repeat that until all the tendons are analyzed, and then you go forward with your final bridge design. That's the concept of it, okay? So as I mentioned before, we use the spreadsheet to make the scores. It's like golf, high score is bad. Scoring is a simple summation. Total available points for given attributes really expresses the weight, as I mentioned. Then there was a couple of these that were given particularly high weight, like the macro environment, scored on a 40-point scale. Other ones, like that didn't have as large of an impact, have a smaller scale, say a 15-point scale. Okay, so the steps are, we determine the risk factor for each tendon or family of tendons if they have similar design characteristics. Locate the tendon on the risk scale and moderate. If moderate or high risk profile is found, consider risk mitigation or reduction technology. Okay, and so if you were to score, and with sort of thresholds are set by that sensitivity study I mentioned before, or you can use a risk matrix that gives you just 16 different categories that you could have, and you just plot where this is according to the scores for the consequence and the risk. Okay, and so what do you do with that? Well, if you have moderate or high risk profile, you want to do some sort of risk mitigation strategy, I think I said this upside down previously, but like implementing EIT, stainless steel strands or carbon fiber strands, basically eliminating the corrosion from the material standpoint, or implement something that'll reduce your risk, like use replaceable tendons or design in replaceable tendons to reduce the consequence side, increase the number of tendons. Those are both on the consequence side, or fully adopt current specifications that would have an impact on a number of different attributes in terms of improving their score. And so the overall concept is that this can be a tool that people can use to help identify the need for these types of technologies. The risk reduction strategies, some of them, they play on a particular attribute. And so those are listed in this table here. And so if you had use, for example, vacuum assisted grouting, you would affect all these different attributes and improve their scores, lower their scores in the case of the way this model works. Okay. The mitigation strategies, again, they eliminate or significantly reduce at least the likelihood of corrosion damage ever occurring, regardless of whether they had the ingress of water and corrosion products into the bridge. So that's the concept. Now, this next section I'm going to go through relatively quickly, just to talk about what these particular tendons are. I wanted to have them in the slides, but I'm looking at my watch and I don't have much time to do them. And they're in the report, so we probably don't need to go through all of them. Just to give you a flavor of what they are, right? There's post-tension tendon profile attributes like length, vertical curvature, vertical profile, whether or not there's conflict avoidance taken into consideration during the design process. Short description of those different ones are there. There's joint enclosure attributes. Now, this is one I did want to show. There's once in a while an attribute, which is a screening attribute, which indicates that the likelihood of corrosion damage is going to be high regardless of any of the other attributes. So, for example, if you had dry joints, which aren't used anymore, but were used at one time, and so just in terms of fidelity of the model, that's included in there. If you're going to use dry joints, well, forget about it. Your risk of corrosion damage is going to be high regardless of what else you do. And so that's a screening criteria. Other criteria are characteristics of cold joints and cast in place or precast bridges. Closure pores, do you have them? How many are there, right? And that's a couple of slides that talk about those, right? Closure pores, for example, the likelihood of water ingress into a duct is increased. The construction joints are introduced at closure pores. And it depends on whether clearance is provided for installing couplers and sealers, for example, being able to adjust the alignment of the sections. If there's lots of closure pores, well, there's additional points assigned in this model. Okay. In terms of materials, things like how the anchorages are protected, what venting protection is used, grout material specifications that are used, how venting is done relative to what is recommended in current standards and guidelines. If it's external tendons, if diablos are used to reduce the likelihood of pinching and things at displacements in the tendon. And so there's a list in these slides, but I'm just going to go through quickly. There's anchorage protection characteristics, venting protection, considering if sealing a grout inlet outlet locations along the duct, and it reflects generally the increased likelihood of metal ducts being breached as compared to plastic ducts. That's sort of in there. And it's screening criteria when venting into the deck, and appropriate specifications for that are not applied. So that's another one with a particular screen. If it was screened up into the deck where it has lots of exposure, you would assume to corrosion products, water and moisture and corrosive agents, then that's going to be a screen. But assuming you don't have that, or you're using appropriate corrosion protection strategies there, then you'd have other characteristics of your venting protection that you would score. Essentially, if you're using PL2 protection levels specified throughout the bridge, or is it PL1, or is there metal ducts, right? That with metal ducts, it'd be the highest likelihood that there was going to be corrosion damage because they're susceptible to the ingresses of water. Okay. There's also insulation quality, construction quality. There's a title wrong right there. That should say quality in that title, but construction quality is a measure. What kind of quality assurance procedures are used? What kind of grouting procedures are used? And are people certified? And are the ducts pressure tested? Is all part of that. And finally, there's environmental attributes. How aggressive is the environment around the bridge? So we looked at that. It's looked at in two ways. One is a macro environment. That's what's the weather outside. And we used characteristics here on the right. You can see them And these are from the most recent work on surface life for bridges, categorizing these in the high, moderate, low. Really, there's 1,000 ways kicking around of characterizing the environments. It's an aggressive, moderately aggressive, or not aggressive environment, essentially. Whoops. And then there's a microenvironment characteristic also, which this is the environment directly around a duct, for example, is at an expansion joint, where if there is the likelihood of ingress of water is increased relative to what it wasn't at an anchorage. Okay, and so that's a microenvironment. It's only in the area of the end of that tendon. And two tendons in the same bridge might have different microenvironments around them. One is exposed at an expansion joint, for example. Another one its end is at a anchorage between segments. And so this particular attribute, it depends on the aggressiveness of the overall environment, right? So those two things are linked together. Okay, so I'm a little over, but just to look at one example bridge, and there's a couple example bridges included in the guide. What we're trying to do here is just sort of synthesize this together, show how it applies and what sort of things affect it on a relatively simple and short example here. The one I'm showing today is a precast segmental bridge. We're going to consider two cases. If you're using current best practices, PL2 and plastic ducts and all this sort of what's available today for good corrosion protection, or you're going forward with say a PL1 corrosion protection level, but with plastic ducts, just to compare the risk values of these two cases. How do they score out? A little bit about this example bridge. The tendon lengths were 135 or 265 feet. So that sort of leads you to where you're going to score in your tendon length attribute. The profile is less than 2 feet of elevation change. There's one closure pore in midspan. It's got a moderate macro environment. The grout materials are class C grouts. The microenvironments, the tendons we're considering are not exposed. So they're not at for example, an expansion joint. Okay. In terms of the consequence attributes, there's 4 tendons per web in this particular bridge we're looking at. And so that the importance is sort of low in that measurement. That's the structural factor that's related to the tendons. How many tendons are in the web, for example, is how that's rated out in different values. There's 4 tendons per web. That's a lot of redundancy in that structure. And so that ends up being low. Easy replacement is high, however, because it's got bonded internal tendons in this case. And we want bridge importance just typical for that. And so that sort of leads you to scores for each of the attributes. In the case one, we're looking at high level of protection, at least 4 levels of protection at the anchorages and things like that. Proper venting for all the ducts, a very effective QA process, pressure testing of ducts completed to ensure a watertight seal. And so we take those criteria and apply them with the attributes in order to develop a score. And so you end up with a scoring sheet sort of like this. It just takes a minute, really, once you've got the characteristics and criteria lined out, and you end up with a pretty low score because there's a lot of corrosion protection. That makes sense. That's what you want it to be. So you got kind of a remote likelihood of corrosion damage. The consequence factor was determined to be 0.67, which is high, not critically high, but pretty high. And that's based on the system factor for the tendons being 4 in a particular web, and that they're bonded internal tendons. And so we end up with a risk level of 11. Okay. In case 2, well, we've got a different set of criteria here. We're only using PL1, sort of typical QA processes. So that results in a higher risk scale, not surprisingly. Okay. And so the occurrence factor for case 2, that should say there's a typo, sorry. For case 2 is 0.49. The consequence factor, same as case 1, is 0.67. So then the risk factor for that bridge turns out to be 32. And so, right, that's just an example of how you do that, right? So you go in, you've got these characteristics of your bridge, you can score it according to these attributes, and you get some value on this risk scale. And the risk scale that we end up using looks kind of like this. Things that score below 40 but above 20 are in a moderate range. Things that score below 20 are in a low range. Right? It's not shown in the colors here, but it's low. Okay, so the action really is in the moderate and high area. So you've got a moderate risk level in that bridge. And so how would you get that to lower risk level? Well, if you implemented some, say, PL2 on the bridge, for example, that would put you down. And so it's really, as I said before, a lot of this is just engineering decision making that people make all the day, formalizing it into a process and methodology that's organized. Okay. If you want to use a risk matrix for that, this is where they plot out on a risk matrix, right? That one is in the green area, another's in the moderate yellow area, case 1 and case 2. And then what if the bridge is in an aggressive environment rather than a moderate environment, as we ran the original version of the model? Well, that increases their score naturally. That's what you'd expect. So both case 1 and case 2 increase. Case 2 increase a little more. But we had, if you plot them on a risk matrix now, it's got up in this sort of higher risk area. And you would need to do more, perhaps, to reduce that risk score down to the low level where you'd like it to be, right? And so in the case 1 here, which is shown by these triangles, they stayed low regardless of the more aggressive environment, with all the corrosion protection strategies largely already being implemented. So, okay, so just a conclusion of that is why case 1 presented something with full corrosion protection to current standards in PL2. It ended up with a low risk. Case 2 had a lower level of corrosion protection than PL1 with typical quality processes, ended up with a moderate level of risk. That was elevated in the case if it was a more aggressive environment. And so that pushed and adjusted a little bit north when you had an elevated or a more aggressive environment surrounding the bridge. So, okay, so that was it. I think I ran a little long, Greg, but hopefully we still got some time for questions. Just to give a little summary and review. So the guideline that was developed, it's available, I think it might be in the link here, was based on a couple of factors, an occurrence factor and a consequence factor, how to calculate those based on expert judgment, make a quantitative model from some qualitative rankings of importance and impact on the corrosion, likelihood of corrosion damage. And with the concept being that elevated levels of risk, once you get now we have a methodology sort of characterizing that and be able to put that on a numerical scale to communicate it and say, okay, well, this is moderate to high risk because it scores 37, for example. Well, we should implement some risk reduction strategies in order to make that bridge a low risk of corrosion damage during the life of the structure. So, that we're using a risk scale essentially to score that in the end. You can also use a matrix if that's your preferred method. The matrix is a little bit, it only has 16 options in it, whereas the number line is kind of continuous, so the number line can be easier to work with sometimes. If you're in the moderate and high area, you want to improve the corrosion protection strategy for your bridges overall. That's essentially what the outcome of it is. So, all right, that's all my slides, Greg. I'm happy to answer any questions if anyone's still awake after that 50-minute.
Oh, outstanding, Glenn. Thank you. Great presentation. And yes, we do have some time for some questions, and we do have, I think, a couple of them. I'm going to introduce real quick, though, our Q&A moderator, Mr. Reggie Holt from the Federal Highway Administration, is joining us today. He's a senior bridge engineer with Federal Highway, and I won't read all his little short bio we have here on screen. But I will share that Reggie oversaw this project with Dr. Washer, and as an industry group, we're very thankful for Reggie in terms of helping the industry move forward with technologies and techniques and practices to improve our processes. So with that, I'm going to turn it over to Reggie. I think there's a few questions that are up in the chat. So or actually in the questions pane. And as we're talking, if you have any questions, go ahead and pop them up in the questions pane as I demonstrated earlier, and we'll quiz Dr. Washer here for a bit. So.
Sure. Thank you, Greg. So we do have a few questions. I guess I want to reiterate that the report can be downloaded in the handout section. We didn't have time to get to it today, but the spreadsheet that was used in the presentation will also be uploaded, and it'll be accessible on the ASBI website along with the slides and all the support information. So that's just for the future use. But a couple questions, Glenn. The first one is dealing with your risk scale. And the question was, is that risk scale, was it set up for the expectations of a 75-year service life? And how would you adjust it if you had a 100-year service life expectation?
It wasn't specifically set up to a 75 or 100-year length. Neither one of those, I think, was a consideration. Because the concept was that this is something that was going to be corrosion damage in the normal service life I would say qualitatively, you were probably thinking about 50 years as much as 75 years, but it wasn't quantitatively linked to 75 years. If you had, we're looking for an extended service life beyond or out to 100 years, and you wanted to make an adjustment to that to move it, to the left slightly in terms of the thresholds, I imagine that would be justified. But the thresholds are set based on rational thought and engineering judgment, and so they're not calculated to a particular value. And so I guess in a sense it's the 75 years if you consider that to be the status quo of what everyone considers the life of a bridge. My sense would be most people probably think about that in terms of 50 years. So, that I think is the answer to that question. So it's not particularly scaled to a particular number.
The other deals with the applicability of this guidance for in-service tendons.
Is that for me?
Well, I mean, I can answer it in a way, and you can. I mean, I guess I'll take that one. That the intent is for new construction. I guess there is some level of applicability to in-service tendons, but recognize that this guidance is intended to steer designers and owners to, I guess, sound durability detailing decisions. So if there was a previous technology that was used, it's going to be biased and it's going to obviously score low, and it may or may not be, I guess, applicable to assessing an in-service bridge.
Yeah, and the main thing that it doesn't have that an in-service, like for a routine inspection risk model, that it has the current condition, and so there's no attributes in here discussing what the current condition of the bridge is, and usually an in-service would have something like that. So obviously if there's rust standing in the bottom, in the soffit of the bridge, the likelihood of corrosion damages increase quite a bit as compared to not having rust standing, for example. So there's no current condition in this model, and I guess my suggestion would be if you did an in-service model, you need to have a couple attributes that described, well, what is this condition now? Because if the deck is shot on the bridge already, yes, that's a better analogy probably. Is the deck on the bridge shot or is it not shot? If it's already leaking into the box, that's going to need to be considered. And so I think the difference between this and an in-service one would be the condition attributes.
Very good. One more. I think you touched on this one. We should reiterate it. It says, is this for a score based on a tendon or based on for an entire bridge?
Yeah, it's based on a tendon, particular tendon. Yeah. So some of the attributes would differ by tendon. So the anchorages, for example, are they in between spans? Or are they internal in the box or external? And so there may be large groups of tendons that can be grouped together if they all have those characteristics the same. But when they were different, or the role of the tendon was different, it would need to be by tendon. So the concept is it's by tendon. Practically implementing it, you can probably group tendons of like characteristics together. Yeah, obviously. So.
Thank you. One more question I have, unless we get another one. It deals with structural health monitoring being identified as reducing the consequences. It asks if we investigated, what type of structural health monitoring or evaluation were we considering, and are they different, or do they affect the consequences differently?
Yeah, there's a lot of discussion of that over time, and it is one way of tracking the condition of your structure, but it really doesn't affect the likelihood of whether corrosion damage is going to occur or not. You could make an argument that it would enable you to maybe repair it, otherwise something that you later would have to replace. But overall, I'd say that was considered very carefully, and is I think even listed as one of the technologies that could be applied, but it doesn't necessarily directly apply to either of those categories. And so it's in a little bit of a gray area. Because it might give you information about that the damage is occurring, but it's not going to affect how likely it is to occur. Without some other stipulation that, well, we're going to use it to, for example, decide to go out and put sealer on the concrete or something, something that would be an additional level of corrosion protection. So I guess my answer is it's not too much into this model, particularly under a specific scenario. It could be implemented in a way that would be useful for it. So I don't know if that answered. That might have been a circular answer. I'm not sure. I'll have to listen to the tape later and see if that made sense. So.
All right. Well, thanks, Glenn. That was the last question we had, unless I guess we are right on time. So, Greg, do you have any parting words?
Yeah, I guess I'll share some last thoughts. Again, thank you, Dr. Washer, for joining us today. I think the work you've done is outstanding, and I look forward to seeing more owners adopt the methodology and individual designers as they work through their projects to kind of do those risk assessments on their tendons and be able to kind of have a methodology to think about what they're doing and perhaps up their game a little bit in a logical sort of way rather than just sort of randomly picking stuff. And so that's outstanding. I appreciate you taking the time to share this with us. As Reggie mentioned, in the handout section, you'll find access to the report that's been written. We will be uploading not only that report, a PDF of the slides, but also when it's available, we'll also put the spreadsheet up on our at that place on our website as well as the recording for those of you who have colleagues who weren't able to attend today, or you want to go back and review. Opportunity to revisit this presentation at any time in the future. Again, just the last reminder about following ASBI on LinkedIn. Our June webinar registration is already open, so if you want to go ahead and sign up for the June webinar, that'd be great. We look forward to talking a little more about segmental bridges and specifically about rail bridges. So with that, I'm done, unless Reggie, you have any last comments to add.
Just thanks for the opportunity to present on the guidance.
All right. Again, thank you, everybody. Have a good day.
Take care.